Here is a standing wave inside a pipe. The wave is actually produced in air contained within the pipe. This thick border on the outside, that's the pipe, and these dots are the air molecules. So you can see there are places where the air compresses, and then at that same spot, the air eventually expands apart. Compression here, and then expansion, or rarefaction. This is the same picture, but now we can also see each particle's displacement. So if I inspect this particle all the way at the edge, right here, see this one right here, see how far to the right it is, and then it gets pushed really far to the left. This particle at the open end has maximum displacement, whereas this particle at the middle, it's not moving at all. We can show those displacements using this graph below. The particle at the left edge goes really far to the right with that positive displacement, and then it goes really far to the left with that negative displacement. But the particle in the middle never moves. If we close one end so that now there's a wall, these particles can't move at all. If they try to oscillate left and right, they bump into the wall. But these particles at the open end, they can move really far. Closed ends where the particles are fixed are nodes. Open ends where the particles are free to move, those are antinodes. As we can see from the animation, sound is a longitudinal wave because it has compressions and rarefactions. But more specifically, we could appeal to the definition of longitudinal waves. When the sound wave transfers energy, the particles oscillate parallel to the direction of energy transfer. So what do you think? Are sound waves more like waves on slinkies or waves on strings? This is like when my nephew hides and we play hide and seek and I see his toes peeking out. I wonder what the answer will be. There's the toe peeking out. Well, before we reveal the answer, a wave on a slinky has compressions and expansions, and a wave on a string has crests and troughs. So clearly, waves in air, sound waves, are more like slinkies. To recap what we've learned already, standing waves form when two identical traveling waves move in opposite directions and they continually interfere. So you have two waves moving in opposite directions, traveling and interfering with each other. But they only form at certain frequencies that satisfy the boundary conditions. When I say boundary conditions, I'm talking about things like particles where you have a fixed end are unable to move. And particles where you have a free end, those particles are free to move. So that creates a boundary condition. Here it is. Here's the fixed end condition. Fixed ends must be nodes. And free ends has a different boundary condition. Those must be antinodes. These special allowed frequencies, the special ones where we can form standing waves, we can satisfy the conditions of the boundary, we call those special frequencies harmonic frequencies. Because standing waves are formed when two traveling waves overlap and interfere, what we get is a wave with a bigger amplitude, and it oscillates between that shape and this shape. But we can still see there's a giant amplitude, twice as big as before. So standing waves have high intensity because they have big amplitudes. And in the case of sound, the intensity tells you how loud the sound is. So standing sound waves are loud. They have high intensity. Flip 2 pages ahead and take a moment to read how standing waves are different from traveling waves. And then let's put down some really important pictures. This is just a reference, so you don't need to draw this. On the left, I have a string, and I'm going to pluck the string so that a standing wave forms. Now the standing wave can have different shapes. It could look like this, or like this, or maybe even like this, or you could continue. What's the difference? Well, in the first case, I'm putting only this much of a wave on the string. In the second case, I'm putting this much of a wave on the string. And in the third case, I'm putting this much of a wave on the string. So I'm increasing the frequency by putting more crests and troughs onto the string. Let's call this n equals 1. This wave is twice as frequent because instead of one antinode, I have two antinodes. So we're going to call that n equals 2 to show it's twice as frequent. This wave is 3 times as frequent as the original. Next we go to the pipe with air. These are both open ends, so they're free. Particles are free to move back and forth. They can vibrate left and right. Those are antinodes. So to figure out what shapes fit, I'm going to put my reference wave down again. Here it is. And I know I have to start at an antinode here, but I also have to end at an antinode. So here's the first antinode I could go to. And then I stretch this shape across the pipe. But instead of stopping at that first antinode, I could stop here instead. And I could stretch this shape across the pipe. Down and then back up. Or instead of stopping at this antinode, I could stop right here. And then I stretch that shape across the pipe. Just like I said, these are nodes because the string is tied down. Those particles can't move up or down. I am stipulating the two ends of this pipe have to be antinodes. And we figure out from there what shapes fit. Just like before, this is n equals 1. This wave has twice as much as we had up here. So we are twice as frequent. And this wave has 3 times the frequency of this here. And you can see because we have half a cycle, and half a cycle 3 times, whereas we have half a cycle only 1 time on top. How about the far right case? Just like before, you can draw a reference wave. This is a wall, so particles are fixed. They cannot move. That must be a node. This is an open end. Particles are free to move, so that has to be an antinode. If we go from node to antinode, the first shape we can stretch across is this. The next shape you'll find is this, and the last shape is this. And instead of counting up 1, 2, 3, you find that, look, we have a quarter of a wave. That's the original shape. And then we have another quarter from here to here, and a third quarter from here to here. So this wave is literally 3 times as frequent as the original. And if you count it up on the bottom, this wave is 5 times as frequent as the original. This business of counting how much more frequent the subsequent waves are is really important. In fact, there's an equation that says the frequency, the equation says the frequency of the nth wave is equal to that harmonic number times the frequency of the very first wave you can produce. In all of these cases, we've only shown one moment in time. If we let the wave evolve, it'll oscillate down to here in half of 1 cycle. Here it'll oscillate to the mirror image, and likewise. And how about for these pipes? Well, the particle on the edge, right here, these particles, will start out with really big positive displacement, and then they'll reach negative displacement, so they'll move this way. And we can sketch out the other extreme for each of these. Always remembering that for pipes, we're dealing with longitudinal waves. We just like to represent those longitudinal waves with sine curves.